All right, question 1 asks us about values from this table. So the first thing it's going to ask us to do on this function for temperature is approximate C prime of 5. So if we want to approximate C prime, then we need to use the slope, because that's what the derivative is going to measure. It's going to measure slope between 3 and 7. So we're going to use these 2 points right here and basically do a slope formula with them. So that'll be change in y over change in x, C of 7 minus C of 3 over 7 minus 3. It's also the average rate of change formula. And so that, no surprise to us, is negative because it tells us the function is decreasing. And it asked to indicate units of measure. So they are looking for units on that. So make sure we label it as degrees Celsius per minute. Since our temperature was in degrees Celsius and then our time was in minutes, it's going to be degrees Celsius per minute. Part B asked for a left Riemann sum with 3 subintervals. So we're going to have 3 different rectangles to approximate that value. And you'll notice that they're all different distances of intervals. So we need to keep an eye on that when we make our rectangles. So we have base times height. The bases are all of different distances. So for example, between 0 and 3, the distance is 3, but between 3 and 7, that distance is going to be 4. And then for the y value, because it's a left Riemann sum, we're going to choose the leftmost endpoint to use. So between 0 and 3, we're going to choose 0. Between 3 and 7, we're going to choose 3. Between 7 and 12, we're going to choose 7. And we get 985 as our approximation for the integral. Then it asks us to interpret what 1/12 of that integral is in the context of the problem. And if we put that 1/12 out in front, that is another way we can write it as 1 over 12 minus 0. That's going to be average value of the function. So the function is temperature, so it's going to be the average temperature over the course of that 12-minute period of time that we're talking about. Average value of the function. Next part, it gives us C prime of t and then asks us to find the temperature. So we have rate of change, we're asked about the actual temperature, so that means we're going to take an integral of that temperature. And we know that C of 12 is 55, so the temperature is at 55 at 12, and on the integral between 12 and 20 is going to tell us how much it changes from that 55 between 12 and 20 to give us our final temperature of 40.329 degrees Celsius. Then for part D, it gives us a second derivative, C double prime, and then asks whether the temperature is changing at a decreasing rate or an increasing rate. Is the rate of the rate, which is what the second derivative tells us, increasing or decreasing? And that's whether that second derivative is going to be positive or negative. And we can see there's a little sketch of the graph of C double prime. C double prime is positive throughout that, so we're changing at an increasing rate throughout. All right, number 2. Number 2 is our particle question. It gives us a function for velocity and then asks a couple of questions about the velocity. So the first thing it asks is that it says there's a time where the particle is at rest, and it says find t sub r. So when is the particle at rest? So we're going to say, well, the particle is at rest. That's a velocity question. So the particle's at rest when that velocity is 0. So we put it in our calculator and find when the velocity is 0. That first time is at 1.4256. That's in that time interval. And then it says is the particle moving to the right or to the left in between 0 and that point? And again, I gave a little sketch of the graph, and you can see that velocity is positive in that time interval that they're talking about. There's velocity being positive, so therefore, since velocity is positive, we must be moving to the right. Part B. Finding acceleration at 1.5. So we need to draw that connection by saying that the acceleration is the derivative of velocity so that they can see how you're drawing that connection. So velocity is negative there, and acceleration is negative at that point. You can see that velocity is negative by that graph, and then it asks us to find acceleration, and we found that that was -1. So both velocity and acceleration are negative. That means that velocity tells us we're moving to the left, and acceleration tells us we're being pulled to the left. So we're moving to the left and being pulled leftward, so we are speeding up. That speed is increasing, and the explanation is going to be that velocity and acceleration have the same sign. The direction that we're being pulled in is the same as the direction we're going, so the speed will increase. Part C, it gives us, it asks about position, and again, it gives us a starting position, that the position at 1 is -3, and then it asks us to find a position at 4. So similar to on the last question, we have that starting position, so therefore position, this is where we start at -3, and then we have our integral that will tell us how much we change by. So if we want position at 4, we start at -3, and then this will tell us, this integral will tell us how much that position changes by from 1 to 4. So that integral is going to tell us that we're slightly to the right of where we started. Therefore, -2.803 is our ending position. It's this -3 is here's where we start. The integral is here's how much we move, and that will tell us where we end up at. Then over in part D, it says find the total distance traveled, and hopefully by now you know that to find total distance traveled, you take the integral of the absolute value of velocity. That's number 2. On to the non-calculator part. Number 3. Number 3 was about differentiable functions. So it gave you a value of dH dt, and we start by sketching out the slope field. The slope field needs to start at this point and then be sketched along. So I gave a rough sketch here of that slope field. I also put that starting condition of h of 0 being 4, wrote that down. So part A is just sketching out that slope field, connecting together our slopes. In part B, it says h of t is greater than 1. So we're going to keep using that in a couple different places here. The h is greater than 1 throughout. From 0 to 5, we need to know where h has a critical point, and then whether it has a max, min, or neither at that critical point. So the critical point is when the derivative is 0 or does not exist. So we're going to take that function and set it equal to 0. There's nowhere that it doesn't exist, so we just need to figure out where it's 0. So first off, we know that h is greater than 1. So this piece right here of h minus 1 is always going to be positive if h is bigger than 1. So we don't need to worry about when that is 0 because it never will be. So we need to look at separately when cosine is 0, which in the interval from 0 to 5, the only place that happens is at pi. So in order to figure out whether that's a max or a min, we look at what's happening to the left of pi and what's happening to the right of pi. And again, we don't need to worry about the piece in red because that's always going to be positive because h is always bigger than 1. So all we need to worry about is when cosine, what cosine is doing. Well, cosine between those values to the left and right of pi is going to be changing from being positive to being negative because of how cosine operates in the first and second quadrants. So because this function is changing from positive to negative, dHdt is changing from positive to negative, that means we have a maximum. And finally, part C asks for you to do your separation of variables. So first, we're going to put everything with h on one side and everything with t on the other. So I'm going to divide by the h minus 1. I'm going to bring the dt over here by multiplying. And then we're going to take our antiderivatives. Antiderivative for the h minus 1 on the bottom will give me a natural log. And then to undo our chain rule, you can do a u substitution if you'd like, but antiderivative of cosine is sine, and then we have the t over 2, and then we put our plus c, plus our constant. There's our constant of integration. And now, the way that I like to do this one is I'm going to solve for h first. So I'm going to rewrite with e to the power of everything on the right equals h minus 1. And I got rid of those absolute value bars because we said h was bigger than 1. So there's nothing I can put into here that will make it negative. So that's why it was safe to get rid of those absolute value bars. So now we have the entire right side up in the exponent, which we're going to say that this is e to the sine of t over 2 times e to the c, and e to a constant is still a constant. So that's how this constant winds up out in front. And then add 1 to both sides. Now over here, we're going to plug in the point. We're plugging in 0 for t and 4 for h, and solve and find that c equals 3. So 3 is the number that winds up out in front in the final answer. So that's our steps for the separation of variables. Number 4 gives us a graph and is going to ask various questions about the graph of f. And it says that g is the integral of f. So one thing to keep in mind when you see that g is the integral of f is that hopefully you're putting, as soon as it asks about g prime, you should put that g prime is f. But right now it just asks us for g of 6, g of 4, g of negative 6, g of 4, and g of 6. So in order to do that, we're going to use areas of this graph because it's asking for integrals. These are all integrals, so we need the areas. So separately up here, I went ahead and found those areas. It already told us that this area here was 12. It said that in the problem. And then we can find, since it said that the graph to the right of 0 is linear, that means that we can treat this as straight lines and use triangles to get the rest of the areas. So this triangle, 1/2 base times height is going to be 4, and then this triangle, 1/2 base times height is going to be -1 because it's below our axis. So for our function g, that's our function for g. G is our integral from 0 to -6. Now, because those bounds are not in our usual order, we're going to flip those bounds and then change the sign. So the negative integral from -6 to 0, that will give us negative, that area is 12. Then g of 4, integral from 0 to 4, well, that's just the area of the green triangle, which is 4. And then the integral from 0 to 6, well, we have the green triangle, but then we need to subtract away that blue triangle that had the area of 1 because it was below the x-axis, so that made it 3. Part B, we're being asked when does the graph have a critical point? So again, the critical point is when the derivative is 0 or does not exist. This is where we're going to say that g prime, the derivative of what we're asking for, that g prime is f. And we're looking for when that derivative is 0 or does not exist, but it exists everywhere in there. So really we're looking for when that derivative, which is that g prime, which is what the function that we're looking for, when is that function 0, which is at 4. On part C, it gives us a new function of h and asks for h of 6, h prime, and h double prime. So the difference in this function is, first of all, we're starting at -6. The bounds are starting at -6. Also, notice that it's f prime now. It's the integral of f prime and not f. And we always want to explain in terms of the graph that they give us. So we're going to say how h is going to relate to f, and how h prime relates to f, and how h double prime relates to f. So first of all, h prime of x is f prime of x, because the derivative of the integral is itself fundamental theorem of calculus. So starting with h of 6. H of 6 will be integral from -6 to 6. So I need the antiderivative of f prime. Well, luckily the antiderivative of f prime is just f. So we take f plug in 6 minus f plug in -6, and it gives us what those points are. Right? Not doing any slopes or areas here because the antiderivative of f prime is f. So we're just reading the graph, plug in 6 minus plug in -6, and we get -3/2. For h prime, as we said, h prime is f prime. So h prime of 6 is f prime of 6. And to get f prime of 6, we look at the slope of this line right here, which is going, because of where we're starting, is going down 3 to the right 6. So that makes it, the slope there, -1/2. Then h double prime is the slope of the slope. It's the rate of change of the rate of change, but we have a linear graph. So that slope is not changing. It is staying that -1/2. So therefore, that second derivative is 0. Because that graph is linear, the rate of the rate not changing at all. So it's 0. Number 5. Number 5 is, I would say, probably the trickiest one on here as far as how to set up and how to approach some of these questions. So starting with part A, it says there's a point near 2, 4 with x coordinate 3. So we're going to store that. We're going to keep that in mind. But here's the key part. Use the line tangent. So we need our tangent line in order to answer this question. When we get our tangent line, that's where we use the slope at that point 2, 4. So it gives us this function and then gives us dy dx. So we need dy dx, the slope, at that point. We plug in 2 for x, 4 for y. And that's going to give us the slope of that tangent line. And we already know what the point is. The point is at 2, 4. So y minus our y coordinate of 4 equals the slope, which we got from our dy dx, times x minus our x coordinate. Now we can use that tangent line. We can use that tangent line to approximate the y coordinate. So when x is 3, what is y approximately going to be? So let's plug in 3 for x. And we get that our approximation for y is at 72/19. Now part B, here's where some of the wording gets tricky. Part B says, is a horizontal line y equals 1 tangent to the curve? So y equals 1. First of all, the y coordinate has to be 1 in order for it to be tangent to the curve, because it has to be on the curve. And if it's a horizontal line, Horizontal line is going to imply that if it's a horizontal line, then dy dx has to equal 0 at that point. Has to equal 0. Now, the only way for dy dx to be 0 is if x is 0. So really, our question is, when y is 1, is x 0? I went in a bit more detail than that, but if y is 1, which has got to go through to be on the tangent line, let's plug in 1 for y, and we find that x is plus or minus square root of 43. And indeed, if you plug in to dy dx there, square root of 43 for x and 1 for y, whether it's positive or negative, you're going to get something that isn't 0. So the tangent line there is not going to be horizontal. So therefore, we are not tangent to the curve. Then part C asks a similar question, but a little bit easier. Because it asks, here's our point, is the line tangent vertical? Now, we have a vertical tangent line when the derivative doesn't exist. So we're looking for, when I plug in this point, is the derivative not exist? And we find negative 2 root 48 over 3. That's messy, but it's not, does not exist. We don't have something over 0. So dy dx exists, therefore tangent line is not vertical. And then finally, part D, a little bit of related rates here. So we're going to take our derivative, and we're going to have dx dt and dy dt whenever we have the derivative. So it's giving us dy dt. It's giving us dy dt right here at the y coordinate is decreasing at this rate, decreasing. So that means that our dy dt is negative. So dy dt is negative 2. It gives us the point of x equals 4 and y equals 2. So 3y squared is our derivative of y cubed. We took a derivative of y, so we're going to write dy dt. And then the second part of that is a product rule. Then we plug in all our other points. We plug in negative 2 for dy dt. We plug in 4 for x. We plug in 2 for y. And solve for dx dt, which turns out to be 10. So that's our related rates idea. We take a derivative of each piece. All right, finally, question 6. Question 6 was about areas and volumes. So part A asked for the area of the region R. So we're going to look at the top curve minus the bottom curve on that to do our integral. So it should be the integral of our top curve minus bottom curve is f of x minus g of x. Then in part B, we have a cross-section question. We have our cross-section being rectangles where the height is half of the base. So when we find that volume, again, we have top curve minus bottom curve, but our bottom curve here, top curve is g of x, but the bottom curve here is 0. So the base is g of x, and the height is just half of that, half of g of x. So we take our integral of 1/2 base times height. These two multiplied together squared. And so I went ahead and did out all the work, but you don't need this much detail. As long as you got to here of plugging in 5 minus plugging in 2 and didn't make any mistakes after that, then you should be okay in what answer you got. And then the last one we'll do is that we have our discs and washers. We're revolving around the horizontal line y equals 20. Y equals 20 is around here. So we're going to revolve around it by making a washer. So I have our washer here. It's pi times big R squared minus little r squared. Big R, our radius here, is 20. And then our little r is our distance between 20 and g of x. So we take top minus bottom, 20 minus g of x for r little r. And then put all that together. Make sure the pi is out in front. It should go from 2 to 5, big R squared minus little r squared. And so that's our areas and volume questions. And that's the entire free responses.